Okay, well, I think we'll get started and folks can continue to pop in as we go through a brief introduction. So welcome everybody. My name is Maureen Gribble and I work with UE Systems, and today we're excited to be presenting Bearing Failure Mechanisms Part 2, Failure Propagation and PDM Technology. We're very happy to have Andy Page of GP Allied here to present this webinar for us. Hopefully most of you were able to join us back in March when he did part 1, and if you weren't able to, we do have the recording of that webinar up on our website, so you can always go back and check that out later on after this webinar is finished. And on that note, I do want to just make everybody aware, and I'll state this again as we go through the presentation for those that pop in a little later. We are recording this webinar as well. So this will be up on our website within a couple of days. So for those of you that want to go back and re-listen to some of the pieces, or have colleagues that just couldn't make it but you think would benefit, that will be up on our website, and we'll make all of you aware of that via email once it is online. So just that quick little housekeeping note for you. So just a real quick overview about UE Systems before we get started. We've been in the ultrasound technology industry for a little over 38 years now, helping our customers throughout the globe with utilizing ultrasound as a part of their predictive maintenance or condition-based monitoring programs within their facilities. We do have support offices throughout the U.S., also throughout the globe, and that's one really cool thing about these webinars is we are able, of course, depending on what time it is for some folks, we are able to bring together customers from all around the world who, whether we're in Canada or India, everybody's kind of dealing with the same kinds of issues, so we're happy to have this forum to bring folks together to ask questions and so on and so forth. So that's why we're really happy to do these webinars on a monthly basis for everybody. On your screen now you'll see our interactive information kit. So this really is a great tool if anybody would like to get this emailed to them. Just a real easy way to get a better feel for the different technologies that we provide, our software, the different training opportunities that we have. We're happy to email this to if you want it. Just shoot me a question or a comment. You can use your panel on the GoToWebinar panel, and we'll be sure to get that to you. So without further ado, I think we will go ahead and welcome Mr. Page to get started, and I just need to switch this over to him and we'll let him take it from there. So thank you, Andy.
Okay, thank you, Maureen. Appreciate the invitation to speak and the introduction, and just want to tell everybody on the webinar, you can pose questions to Maureen, and she's going to be the person that kind of looks through the questions, and if she happens across one that looks like a good one and looks like one that everybody would want an answer to, she's going to just stop me wherever I am and ask the question. And for the rest of you, I think she's going to get me a copy of the questions, and I'll do my best to email you the answers over the next week or two. So is that correct, Maureen, or did I misspeak?
That is correct.
Okay, super.
Okay.
All right, great. So this is Bearing Failure Mechanisms Part 2. Like Maureen said, last March we did Part 1 and received a bunch of emails. Apparently it was a subject that a lot of people have a lot of interest in. So we decided to do Part 2 and try to extend some of the lessons, if you will, some of the topics a little bit deeper. And as a bit of a review, we will cover some of the same material from last March, but I'm going to cover it much faster, not to as great a depth, and it's going to be covered as something as a review because it's going to help set us for some of the extended conversations we'll have. So
hey, Andy, I'm sorry to interrupt. I've got a couple folks that are chiming in that your volume is a little low. I hear it fine, but that could be because, we're organizer or panelists, so maybe if you could turn your volume up, that would be great.
Sure. Let me do that now.
I think we're good. So why don't we just keep on rolling, and folks that are having a harder time hearing, we'll have the recording, or maybe if you try turning your speakers up a little bit, it might help. All right, thanks.
Okay, great, thanks. Okay, so as a bit of a review from last time, we talked about how rolling element bearings mechanically fail and how they chemically fail. So to continue our review, here we have an outer race, and we have two of our rollers or balls, whichever it may be, and we've kind of frozen them in time. And what you're seeing beneath the balls is what we call a stress cone. And this is the effect of whatever kind of load you have on the shaft. The shaft is pressing down on the inner race, which is pressing down on the rollers or balls, which is pressing down on the outer race, which is being held by the machine foundation. So what happens is we get pressure. The balls or rollers are putting pressure down on the outer race. Of course, they're also putting pressure up on the inner race while they're in the load zone. So you can imagine here's two balls or rollers in the load zone, and these stress cones beneath them is how much stress or pressure or force they're putting on the outer race. And you can imagine in your mind the flip side above them, they're doing the same thing on the inner race. So what happens then is if we were to follow this spot right here where my mouse is, and we watch the rollers, the balls and rollers go past that spot, every time a roller or a ball passes a given spot on the inner race or the outer race, there is a compression of the face of the race. And when that ball passes, that compression is relieved. And then the next ball or roller passes, and it compresses and relieves and compresses and relieves. And in our last seminar, we talked about how often does that happen in one day. And I showed this slide last time, but I didn't go into great detail about this second bullet point, and I'm going to this time for those of you who are interested in such things, because it bears on our discussion later on in this presentation. So here's how it works. For a shaft turning 1,775 RPMs, we just divide that by 60. We know it's turning 29.583 revolutions per second, or we say cycles per second in this case. Now, for an inner race, let's say we had an inner race fault, a function of fatigue, or perhaps a function of contaminants that have gotten into the bearing, and the contaminants have damaged the inner or outer race, or in this case the inner race. What we know from the geometry of the bearing, and I'll explain how we know in just a second, but what we know from the geometry of the bearing is that 8.193 balls or rollers will pass a given spot, any given spot, on the inner race during one revolution of the shaft. So what this means is when there is an inner race defect, like from fatigue or like from contamination, when we collect vibration data or when we look at the ultrasonic data in a spectrum, we're going to have a signal or a peak, and we'll get into this in a little bit, at that frequency at 8.193 times turning speed. So in this particular case, whatever 8.193 times 29.583, that would be our frequency in cycles per second, or hertz, right? So more on that later. So we're asking ourselves then, how often does a given spot on the inner race get compressed, relieved, compressed, relieved? Well, it's about 21 million times a day, or if that machine ran 24/7, it'd be about 7.5 billion times per year. So mechanical engineers in the audience understand that there is no metal that can handle cyclic fatigue forever. That all metals, regardless of their composition, will and do have some cyclic fatigue limit. And what happens is we start to get that subsurface cracking that we talked about last time, and we'll show some pictures of it here in just a moment, right? So how do we know that 8.193? Where did that come from, right? A lot of people believe that things like vibration and ultrasound are more of an art than a science, and they don't understand that everything we do is a function of calculations. It's not a function of gut instinct. It's not a function of, more often than not, it's not a function of what it looked like last time. It's a function of what does it look like at this moment. So if we know the number of rollers or balls, if we know the roller or ball diameter, if we know the pitch diameter, if we know the contact angle of the bearing, and we know the shaft speed, then we can calculate the specific frequencies at which an inner race defect will show up, an outer race defect will show up, a defect on one of the balls or rollers, or a defect on the cage itself. And the cage, for those of you who've taken a bearing apart or seen pictures of bearings, the cage is the little device inside that keeps the rollers equidistant from each other, specifically when it's not in the load zone. So the equations look like this, and we won't go into them in too great a depth, but I'll just read the first one there.
Hey, Andy, I was just going to, it doesn't look like your slides are moving, so I don't know if you paused your screen. There you go.
Oh my goodness.
Ah,
thank you very much.
no problem. A few folks were asking. I was like, well, I want to make sure he's...
I apologize for that.
There you go.
Thank you.
Perfect.
Okay, great.
Okay,
sorry
thanks.
about that. All right, so there's our 7.5 billion times per year. Sorry about that, folks. Here's the information we need about the bearing: the number of rollers, ball diameter, pitch diameter, contact angle, and shaft speed. This probably makes a lot more sense now that you can see my slides move. All right, so there's the equations. And like I said, we're not going to go into them in any great detail, but I will help you understand that NB means number of balls, S means speed, BD means ball diameter, PD means pitch diameter, and cosine theta just means cosine of the contact angle of the bearing. So the interesting thing about this, a couple things, is one, these are very specific calculations. These calculations do not change as we move from one bearing to the next, to the next, to the next. As long as we're talking about rolling element bearings, then these equations remain the same. Now, of course, the result of the equation will be different because different bearings have a different number of balls. You may be turning it at a different speed. The ball diameters, of course, will be different. The pitch diameters will be different, and the contact angle may be different depending on the type of bearing. So for those of you who always wondered how it is they specifically know which part of the bearing's bad and so on and so forth, this is how it's done. Now, for our conversation here, these equations don't change simply because we switch from vibration to ultrasound or from ultrasound to vibration. The equations remain exactly the same. And in fact, a lot of things remain exactly the same, and that's what this webinar is, one of the intents of this webinar is to show. So we will get, these equations will come back into play a little bit later on in the presentation. So as these rollers pass by a given spot on the inner or outer race, we get this subsurface fatigue, these little cracks just below the surface that when we look at it, looks like a discolored track down the center of the race. And for those of you who were on the last webinar, I showed a few pictures of this. For those of you who hadn't seen it, I encourage you to download the last one and take a look. There's some pictures, real-life pictures of bearings, and you can see the subsurface fatigue. You can't feel it, but you can see it, you know, if you were to take these bearings apart. Now, what we know is if we leave this subsurface fatigue, we know that those cracks will propagate and they will eventually connect, and if we continue to leave it, that big chunk pops out. Right? And now we've moved from subsurface fatigue to this thing called spalling. Right? So our first sign of trouble is this subsurface fatigue. Now, since we're talking about failure propagation in the bearing, this is the very first sign of trouble. This is where the bearing defect begins. This is what it looks like when it's brand new. Of course, when it's brand new, there's only one of those subsurface cracks. But we leave it, and more cracks start to appear, and then the cracks start to connect, and then it pops out, and then we've got spalling. So as we talk about these technologies and how they can detect these bearing defects, I want you to keep in mind that this is our first sign of trouble. This is how the bearing defect began. Now, this is why ultrasound works really, really, really well finding these early bearing faults, because as the roller passes over this spot, I get a little bit of relative movement inside each one of those cracks. Right? As the pressure, as the stress cone from beneath the roller or bearing passes over that spot, I get a little movement from one side of the crack to the other. So it's a very high pressure, and it's very small movement. So in the frequency world, high pressure plus small movement equals high frequency. And that being a specialty of ultrasonic equipment, ultrasound is a very nice tool for picking up this type of failure. However, and I'm going to let you hear one of these here in a moment, it doesn't, when we've just got subsurface fatigue, in the ultrasound with the headphones on, it doesn't sound rough. It doesn't sound like we're used to hearing ultrasonic, like we're used to hearing bad bearings when we go to an ultrasonic training class, or when we go out into the plant with the guys who do it and we put the headphones on and they said, yep, this bearing's bad, right? And you can hear the rough pattern of the ultrasound. When we've just got subsurface fatigue, when there is no spalling, you don't hear that rough pattern. What you hear still sounds like clean noise, it's just louder. And that's one of the mistakes we see people make all the time in the field. They will set their volume or their sensitivity depending on which model you're using. And they'll be running their routes and they'll be listening for bearings, or for bearing defects, and everything sounds good and normal, and the next bearing good and normal, and the next bearing good and normal. And then they'll get to the next bearing and it will be significantly louder. And the very first thing they do is they reach up and they turn that volume down, or they turn that sensitivity down. And when they turn it down, they hear that the pattern is still very smooth, doesn't sound rough, doesn't sound random. It's very smooth white noise, and they go, oh, it's just louder. Well, the bearing's actually trying to tell them something. The bearing's trying to tell them one of two things. A, I need some grease, or B, I've got subsurface fatigue. So,
Andy, I think your slide's paused again.
no, I haven't moved it.
Oh, you haven't? Oh, okay. All right. I just had like a bunch of people that were questioning that it didn't seem like you were moving the slide. Okay. I'm sorry. Okay.
No, we're still talking about subsurface fatigue.
All right. Okay.
It's hard to have a PowerPoint slide picture of what an ultrasonic signal sounds like.
All right. Sorry about that. So everybody, we're good. Keep moving along.
But hey, what we know, Maureen, is that we got at least a group that's paying attention and are listening. So
they are locked in. That is for sure. Okay. Thanks.
Okay. So more on that failure propagation a little bit later. So you guys are obviously watching me and wanting to make sure that the slides move. So here we go. All right. So things that we do, and this was in the last presentation, things that we do as asset owners that accelerate that fatigue are things like imbalance and misalignment, and our V-belts being too tight, and broken bolts or loose bolts, broken welds, overload, overspeed, shock load. Now here's the interesting thing about all of these accelerators, and this is something we didn't mention in the last presentation. All of these accelerators, 201, are very low frequency defects, right? Imbalance is a defect. It's not a bearing defect, but it's a machine level defect. Misalignment is a machine level defect. V-belts being too tight is best defined as a machine level defect, so on and so forth through most of those. And the interesting thing about this is that it is these low frequency defects, these low frequency events, that actually create the high frequency problems that we know as bearing defects. Now, this isn't all of them. I mean, poor lubrication will cause them, water will cause them, contamination will cause them. But if we're talking about mechanical drivetrain defects, this is a very nice list of accelerators, or what I'm calling accelerators, things that create these bearing defects that we're looking for, right? So this is our first lesson in condition monitoring technologies, is there is a cooperation between the technologies to help paint a very complete picture of the health of your equipment. And what we're looking for are we're still looking for those high frequency defects, but we're also looking for these low frequency accelerators. Because if we're going to use our condition monitoring program to help us identify and eliminate root cause, then we can't just be looking for the bearing fault, because as you can deduce from this list, a bearing fault more often than not is not the problem. The bearing fault is the symptom of the problem. Here are a list of problems. Let the machine run out of balance, creates a bearing defect. Let the machine run with a misalignment, creates a bearing defect, so on and so forth. So when we think about failure propagation or defect propagation, we don't want to just go back to where the defect began. The most ideal solution would be to go back to the event that caused the bearing fault. All right? So more on that here in just a little bit. So that was how bearings mechanically fail. A small review on how bearings chemically fail. When we mix grease and steel and oxygen and heat, we get this thin layer of iron oxide. And this thin layer of iron oxide is a normal thing. It happens in all bearings. We want it to happen. We count on it to happen because this is the thing that allows the bearing to run at much lower temperatures, because the iron oxide is softer than the parent metal below. So that allows our lubricant wedge there, this triangle thing, this allows our lubricant wedge to ride on this thin film of iron oxide. And this was all covered in detail in the previous presentation. So things that we can do to accelerate this type of wear, and the wear comes from the fact that the lubricant wedge wipes away thin layers of the iron oxide, so the bearing goes down here to the parent metal, grabs another layer of virgin steel, and keeps a thin layer of iron oxide between it and the lubricant wedge or the roller all the time. So as the lubricant wedge wipes away some of the iron oxide, the bearing goes down and gets more virgin steel to create a thicker layer of iron oxide, and eventually the internal clearances of the bearing open up and the bearing gets loose, right? So things that we can do that accelerate this type of wear, called adhesive wear, is we can put too light a grease or oil in there, or too heavy a grease or oil in there, or of course water that makes the lubricant wedge impossible to form, and we wind up getting the roller riding directly on the race, which is a no-no in the bearing world. Contamination, same thing. We get just a small piece of dirt in here, or in this case silica, and it only has to be a little bit thicker than this thin film of iron oxide to cause damage, and this thin film of iron oxide is only 1 to 3 microns thick. So it only takes a very, very small piece of dirt or contaminant to get in there. That lubricant wedge grabs it and plows with it, and pretty soon we've got all these little, they look like scratches, but they're more like gouges in the face of the race. And as far as the bearing is concerned, that works just like spalling, and it propagates itself very quickly throughout the bearing, right? So some of the things we do that accelerate that type of wear, called abrasive wear, are not managing our seals properly, not managing our lubricant properly in terms of the way we store it and the way we handle it, the way we top off the reservoirs and that type of thing. So there ends the review from our previous webinar. Just a little reminder for those who maybe hadn't messed with it since March, but those are the way bearings fail. So we're going to talk about different aspects of vibration and ultrasound and a little bit of thermography and how we use those to help us with this concept of defect propagation, and how we use those to our advantage in our maintenance and reliability program. First thing, couple things we need to get out of the way first though. Slow speed analysis, always a popular question when it comes to vibration and ultrasound. We get this question all the time: which is better for slow speed analysis, vibration analysis or ultrasound? Right? Now, there is this movement out there that says, oh, we like the ultrasound because it's quick and easy. Well, there's a trap here, and I want to make sure everybody's aware of the trap so that you don't fall into it, right? Both are powerful inspection methods for slow speed analysis on rolling element bearings. However, technical note for you to remember, the time capture has to be sufficiently long regardless of which method you're using. And let me explain that in a pretty high level of detail. For ultra slow speed bearings, things turning less than 30 RPMs, and that nothing magical about the 30. Ultra slow just means ultra slow. The cage tends to be the first thing that gets damaged in ultra slow bearings, and that has to do with the rollers sliding instead of rolling through the load zone. And when they slide instead of roll, what happens is the cage winds up having to push the bearing, and it's not designed to push the bearing through the load zone, and so the cage gets damaged quite easily because most of the time the cage is made of brass or some softer material. So the cage gets damaged first, and then the rest of the damage propagates later, right? So the problem with cage is the cage frequency is the lowest frequency bearing fault. It's the lowest of all the bearing fault frequencies. Cage frequency happens about once every 3 revolutions of the shaft. And if I were to show you the cage frequency for a bearing, you would find that it's generally around 0.413 or something like that for most bearings. So that's 0.413 times turning speed, which means I'll only hear cage once every 3 revolutions of the shaft. Now, I'm only hearing cage once every 3 revolutions, whether I'm using an accelerometer that's connected to a vibration data collector, or whether I'm using an ultrasonic contact ultrasound. It's still, cage only happens once every 3 revolutions, regardless of which technology I'm using. So I know I need 4 data points to resolve cage frequency in the spectrum. And for those of you who haven't seen spectrums, we're going to have some coming up. You can create a spectrum in vibration. That's how vibration works. And you can also have a spectrum of your ultrasonic data. And I think we might even have some of those coming up. Go ahead, Mark.
Yep. Someone was just wondering if you could explain a little bit more about what cage faults are.
Okay. So for those of you who have taken a bearing apart, I mentioned this earlier, the cage can be plastic, it can be steel, it can be brass. On the bigger bearings, it's usually brass. So the cage is the thing that, when the balls are not in the load zone, the cage keeps the balls equidistant apart. It basically keeps them from bunching up and making a mess, right? As the balls or rollers go through the load zone, just the force of the being in the load zone keeps the balls rolling, and the cage really doesn't do anything in the load zone. So a cage fault would be, I've got a flat spot on the cage. I've got a nick or a burr on the cage. One of the rollers has been rubbing against the cage incorrectly. It essentially happens when the cage has to start pushing the balls or rollers through the load zone. That's generally when the cage faults happen. And a cage fault is literally the cage getting damaged, right? And the cage is not designed to push the balls through the load zone. The inner and outer race take care of that. So the cage is designed to hold them equidistant when they're outside from each other, when they're outside of the load zone. So just think of a cage fault as basically a flat spot where there's not supposed to be a flat spot, right? On the brass cage itself, or the plastic cage, or even the steel cage. Lots of them are made out of steel. So when we're creating a spectrum, there's lots of rules around the data acquisition, signal analysis, signal processing that used to create a spectrum. And at least that same frequency with this same phase relationship to other frequencies has to appear at least 4 times for us, for the FFT process to realize, hey, that's a signal, that's a peak, that belongs in the spectrum, let's put that in there. So we have to hear the same frequency 4 times for it to appear in the spectrum, which means I need a minimum 12 revolutions of the shaft to be able to see the cage frequency, or in other words, detect a cage fault in a bearing? Well, if I have a shaft that's turning 9 RPMs, I'll need a time capture of 1.33 minutes. And once again, for emphasis, it's 1.33 minutes, whether you're using a vibration analyzer or whether you're using an ultrasonic device. It's still 1.33 minutes. Now, with the ultrasonic device, usually, if we're using one of the older ones, or we're not using the spectral capabilities of the newer ones, we're trying to listen for things that sound rough. Well, you can imagine how difficult it would be to listen for 1.33 minutes and hear 4 tiny events equidistant apart and be able for your brain to recognize that there were 4 events and they were equidistant apart. It's impossible. And we don't have to worry about that because that's why we have a spectrum, right? So the spectrum does that work for us. So bear in mind, you cannot stick your ultrasonic device on a bearing, listen for 10 to 15 seconds and go, ooh, I think this bearing has a cage fault. It's not possible, right? So that's why you have to use the spectral capability of a UE device, or ultrasonic device, sorry, or you have to use a vibration analyzer if cage is an important thing for you to find on the bearing. So with respect to which technique should be used for slow speed bearings, it's usually a function of criticality. The more critical the bearing, the more concerned I am about finding cage defects and finding them early. The less critical the bearing, I may not worry with a cage defect. I may wait for a inner and outer race defect or a rolling element defect that I can easily hear in 10 or 15 seconds with an ultrasonic device. So my answer to which is better has everything to do with the criticality of the bearing you're checking. Right? Okay, so remember, slow speed analysis, specifically ultra slow speed bearings, less than 30 RPMs, you really, really have to use spectral analysis to find those defects early in their defect progression and have the maximum amount of time to deal with them. Okay, an example. Here is the vibration analysis of our vibration data from a 10 RPM shaft. And now it's scaled the same as the bad bearing that I'm going to show you on the next slide. So it looks kind of funny in this picture. You can see there's nothing in the spectrum and there's nothing in the waveform, very, very low, which is exactly what we expect to see on a 10 RPM bearing. However, we move to one of the other bearings on this same machine and we find that there are lots of things going on. The spectrum is full of activity. We'll talk about the activity in a moment. And the waveform is full of activity. And you can see in the spectrum we have all these little blue spikes. And for those of you who are not familiar with vibration data, these are called peaks. So we have all these little blue peaks. And we have identified in this region here, with its harmonics here, 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 and there, we've identified what looks to be an interrace defect. And the further analysis did verify that it was an interrace defect. So here's a really good example of vibration analysis on ultra slow speed. We're showing it looks good there. One of the other bearings on that same machine looks bad, and it absolutely was an interrace defect. Okay, so for those of you wondering how we know it's an interrace defect, well, one of two ways. We can either look up the bearing number and find all that information we were talking about earlier in the presentation, the number of balls, the pitch diameter, the ball diameter, the shaft speed, and contact angle of the bearing, and we can run those numbers through those calculations, and we can calculate what the interrace defect frequency is. Or we can look at these things called side bands here. These little side bands are about this peak, and we found that those are turning speed side bands, and only interrace defects have turning speed side bands. So even without looking up the bearing number, your good vibration analyst is able to determine whether or not it was inner or outer race, if that's pertinent to the situation. Most people don't really care if it's inner or outer race. They just want to know if it's bad so they can get it changed, which I think is the right attitude to the whole thing. All right. So let's talk a bit about fault progression. And fault progression is kind of what brought us in, was the title of this webinar, and it's kind of what got us all here at the table today. So when we talk about fault progression, we're talking about how a rolling element bearing defect begins and then how it gets worse over time, and how those signals that it's giving off change as it gets worse, and how we can collect those signals and analyze those signals using things like vibration analysis or ultrasound or thermography. Now, before we talk about propagation, though, before we talk about propagation, a bit of warning. There are a lot of people who are very, very interested in this concept of defect propagation because they're really interested in this thing called prognostics. For those of you who don't know that term or not familiar with that term, in the vibration and condition monitoring world, prognostics has to do with trying to figure out how much time is left on that particular bearing. Meaning, someone has identified a defect, and invariably someone asks, well, how much longer will it run? Because I'm not real sure what they're trying to do. Maybe they're trying to make it to the end of a production run or something like that. And there are a few systems in the world that absolutely are expected and designed and engineered to run 9, 10, 11 months straight with no down day, no interruption whatsoever. But they are very, very few, right? But in those environments, there are people spending time and money and research efforts trying to derive some type of prognostics algorithm whereby they can collect certain pieces of information from the machine, certain vibration characteristics, and run it through this algorithm and determine how many days are left. So there are some rare instances where that is being researched and progress is being made. However, let me give you some of the challenges they're going through. First, we got to talk about bearings and grease, right? So the question to the group is, and I know I can't hear you guys, but the question to the group is, do bearings consume grease? Or as we say, do bearings eat grease? Now, as you're thinking about that, some of you are probably saying yes, some are probably saying no. Well, the following question is, if they don't consume grease, why do we have to keep adding grease to the bearing? And it's funny to look, you get on some people's faces when we pose this question, because they're like, well, I don't think bearings eat grease, but at the same time, I do know that we have to keep adding grease to the bearing, so where does it go? Well, bearings don't consume grease. That's silly. They don't eat anything. Bearings expel the grease. The bearing design is such that as you put grease in there, that grease is going to go through the interfacing surface, the interfacing zone between the roller and the races. And while it's in there, there's going to be some heat in there. The heat gets transferred from the bearing, specifically in the load zone, to the grease, and then when that grease moves out of the load zone, the grease can dissipate the heat to the air that's in the bearing. Now, at the same time, that grease is also catching, if you will, contaminants that may have gotten into the bearing because of seal damage or because of poor lubrication practices, and we actually pumped contaminants in when we pumped in the new grease. So the grease's job is to remove the heat and the contaminants from the load zone, from the interfacing spot between the balls and the race. So bearings their design is without a seal or some kind of something on there, they will purge themselves of the grease. The bearing actually expels the grease, and that's its effort to get the heat and the contaminants, or the design is such that it takes the heat and the contaminants out, right? So the rate at which it expels grease is a function of shaft speed, shaft load, temperature, and humidity. So if I want to accurately predict how a bearing will respond to a given defect, I have to have a very stable environment, meaning speed, load, temperature, and humidity has to be extremely stable so that I can know the rate at which it's expelling grease and the rate at which the defect is going to progress through the load zone and so on and so forth. So where I do not have a stable environment for speed, load, temperature, and humidity, this concept of prognostics can be quite challenging, in some cases almost impossible. And we know that there are very, very few instances in the world where speed, load, temperature, and humidity are constant. If they were more constant, prognostics would be easier. We also need to talk about bearings and heat. And there are lots of folks out there and taking classes and teaching classes and everything, and in their minds all bearings lock up, and that's just simply not the case. If we look at temperature and we say, well, if that's representative of the normal bearing temperature, we do know that there is some upper temperature where if the bearing reaches that temperature, it will lock up, it will seize, because everything swells in the bearing, the inner race, the outer race, the shaft, the balls, everything swells to the point where the internal clearances are gone and the bearing actually stops. Well, some bearings actually do that. As they get a defect, their temperature will rise and it will start to accelerate, and it will reach some point where the bearing locks up. And if every bearing acted that way, prognostics would be easier. But every bearing doesn't work that way. In fact, most bearings don't work that way. Most bearings, their temperature will rise as they get a defect, and then that temperature will kind of level off as that defect kind of takes its home and the bearing, and it kind of come to an agreement, if you will, right? And then after a while, the temperature goes down and will actually level off, and it will be lower than the normal operating temperature. And this confuses a lot of folks because their paradigm about bearing failures is that all bearings get hotter as they reach failure. Well, not necessarily true. All bearings get hotter as they reach a fatigue failure, or some bearings get hotter as they reach a fatigue failure. Most bearings don't lock up, they loosen up. So the fatigue failure has created spalling. The spalling propagates around the inner and outer race. Material is continuously removed from the inner and outer race as the spalling gets worse and worse and worse. So as the spalling gets worse and worse and worse and material is removed from the inner and outer race, the internal clearances of the bearing are loosening up. So this, if the bearing were to heat up more, it's got more room to expand now, right? So because it has more room to expand, it really doesn't heat up. It just continually eats itself away and it loosens up, right? So if all bearings locked up, prognostics would be quite easy, or significantly easier than it is now. But unfortunately, most bearings don't. Most bearings loosen up. So as we understand that most bearings loosen up, don't lock up, this concept of prognostics gets more difficult. All right, so prognostics is knowing when the bearing will fail, and it is nearly impossible. It does require a steady state of temperature, humidity, speed, and load, and it's only to date, in terms of research and technology, it's only rare cases where this is really possible with any degree of accuracy. So it's only in rare cases that prognostics is possible. So if you're thinking about, hey, I'm going to join this webinar and I'm going to see, somebody must have figured out this prognostics thing, and they must have figured out that when a bearing has 17 Gs and it's running at this speed, that we've got 43.2 days left before we have to fix it. It's not that kind of webinar. So hate to disappoint you if that's what you came to see. However, we are going to talk about failure propagation, and we go back to our old faithful mental model of the thing called the P to F curve. So P is this point up here where the defect enters the system, the point at which the subsurface fatigue begins in the bearing. Point F down here is the point of catastrophic failure. For those bearings that lock up, that of course would be the point where the bearing locks up. For the bearings that loosen up, that would be the point at which the bearings have loosened up to a point that something binds, and because it's loose, it binds and then it breaks. Right? So as this bearing continues along its P to F curve, it's going to give off different signals. Now this is a simple artist rendition of those signals. We'll get a little more specific here in a moment. But you can imagine the subsurface fatigue beginning here, the subsurface fatigue getting worse here, it moving to spalling here, the spalling starting to propagate around the bearing here. It propagates to the point that we can hear the bearing roaring in just with our naked ear. Propagates to the point where things are heating up, the bearing's hot to the touch, and then from here maybe it locks up, maybe it loosens up. Hard to know without knowing specifics about the bearing. Now, if we want to look at that in a different way, imagine taking this P to F curve and breaking it up into three zones. That looks something like this. So zone 1 would be kind of up here where we've just got that subsurface fatigue, where we just have, that's really all we have. Zone 2 would be where the spalling has begun, and then zone 3 would be where the spalling is propagated severely and the bearing is heating up and that kind of thing. So again, just an artist's rendition of splitting the P to F curve into three, should be three equal zones, but this works for the conversation, right? Another way to think of it might be this. This is a little bit more even if you wanted to think of it in terms of severity. When we're in this light pink zone up here, we are at very low severity, meaning the bearing has shown some defect, but it's, in the defect propagation continuum, it's very early, right? And then here, we can start to hear it, becomes hot to the touch, starts to get mechanically loose, and then down here in zone 3, ancillary damage is occurring. Seals are getting damaged, rotors are getting damaged, housings are getting damaged, that kind of thing, because the bearing is so loose, or because the bearing locks up and starts twisting shafts in half and things of that nature. So for those of you who are tuned into the whole work order system, maybe it's easier for you to think of a P to F curve split up into 5 priorities, right? So priority 1 being the worst, down here where that ancillary damage is occurring, and then priority 2 just above, and so on and so forth, over to priority 5, where it is a low priority problem because the severity of the defect is really not that severe. So the sense of urgency does not have to be so high because we do have some time. Right? So as far as a mental model goes of severity, maybe one of these 3 slides works for you. So this slide actually is one of my favorites, because as the signals change from the bearing, we get a pretty nice indicator of what the work order priority needs to be when we put that work order in the system. And we can think of it like this. In zone 1, ultrasound is a very nice tool to find the bearing defect in zone 1. And we know from the ultrasound that it's still fairly clean noise, it's just louder. And that's that subsurface fatigue screaming at us, saying, hey, remember, it's high pressure, small movements, which makes super high frequency noise, right? But it's clean noise. So the bearing sounds clean, but it's just louder, so it's telling us something. The vibration analysis can detect it up there, but you can't use regular standard vibration analysis to find it up there. You have to use this technique called envelope demodulation. And if you have an analyzer that was manufactured or designed and manufactured since 1996, you probably have a vibration analyzer that has an envelope demodulation routine. Now, every manufacturer calls their demodulation routine by a different name. And I'm not going to go into any of the names because I don't want to make it a commercial, but if you look up on their website, you'll find it very easily. You call one of their sales folks, you'll find it very easily. And you have to use that envelope demodulation to find those bearing defects up in zone 1. Because of that subsurface fatigue, there's no spalling yet. There's no hole for the roller to fall off in and make that big bang for the vibration analysis to find easily, so you have to use this technique called envelope demodulation. Right? When we move into zone 2, ultrasound still works great. It's a quieter but rougher noise. So the volume has dropped significantly, but the quality of the pattern has changed significantly. It now doesn't sound like clean noise. Now it sounds like things bumping and things hitting each other, and you can hear that rough pattern in there. So ultrasound still works great in zone 2. In zone 3, your normal vibration analysis, normal signal analysis works great because we now have that spalling occurring on the inner and outer race, and it's very easy for vibration to pick that up. No envelope demodulation required. In zone 2, the bearing is starting to warm up. Early in zone 2, it's just maybe a few degrees, but by the end of zone 2, it's a significant increase in heat, and it's easy to tell that the bearing has an increased level of friction inside of it due to the spalling and the balls bumping in and out of the holes created, the spalls, right? So starting to warm up. In zone 3, now the bearing's very rough. It can be very hot. Of course, ultrasound finds it easily. Vibration finds it easily. Infrared thermography finds it easily. If you're the kind of person that likes to lay your hands on the bearing, I don't suggest it, but if you are, you can find it very easily because it will feel rough, it will sound rough, and it will be, more often than not, it will be hot to the touch. Some bearings, those bearings that are locking up, will get extremely hot, which is why I don't suggest putting your hands on it. You can get a spot pyrometer now for $60, so no need to put your hands on something and risk getting hurt. So the concept of fault progression and how it relates to the rest of our maintenance world is actually the most important thing of this entire webinar, right? If we look at the work execution management concept, a work execution management work stream, if you will, it has the following elements, right? There's work identification. That's how work is identified out in your facility. There's work approval, which of course is how work requests get turned into work orders and who approves them, and and who does all that stuff. There's work management, which has to do with the way we manage the backlog and how we prioritize the work and how all that other stuff. There's work planning, work scheduling, work measurement, how we determine whether or not our loads are balanced around the facility, and loads are balanced between crews and stuff like that. And then there's how well we use the CMMS package to manage our work execution effort. Now, where does condition monitoring come in? The vibration, the ultrasound, all that stuff, it comes up here in work identification. Work identification arguably is the single most important element of work execution management, because if I do not identify the work, then there is no work to approve, to manage, to plan, to schedule, or to execute. All right, so work identification is where it all begins. Now, if I have the type of inspection program that finds these machinery defects very low on the P2F curve, what have I done to the rest of the work execution management schema? Well, I've just tied one hand behind my back and I have to hop on one leg because I just shortcutted all the time that the rest of the process needs to work. So the intention of condition monitoring, the intention of educating ourselves about failure propagation is not so we can know how many days we have left. It is so we can understand, am I identifying these defects as early as possible in their defect progression cycle, thus affording myself all of the time I need to comfortably approve the work, manage the work, plan the work, schedule the work, and execute the work. So the use of condition monitoring tools like ultrasound, vibration, thermography, and the concept of failure propagation is all about improving the work identification function inside the work execution management effort. Right? That's why we're here. That's what this presentation is all about. Let me give you a very detailed example for those of you who like really detailed examples. If our inspection program is working like it's supposed to be working, we will find those defects and we will initiate that work request very, very early, and it's still a priority 5, right? Now, as our work execution management process, which is all these words here, as they start to work, that defect's still out there, and it's not getting better. it's getting worse, right? We know this. So we take a little time for the work request to get received and converted to a work order. Well, all the while, my defect has gotten a little worse. And you could visualize the P to F curve, and you could visualize this defect moving its way down the P to F curve instead of moving its way along these arrows. It's the same thing, right? The job is researched and the necessary parts identified. Purchase request is entered and approved. Parts are ordered. It takes a little while to build the job plan, so the job plan gets completed. The parts are received. The parts are kitted. The work order is released for scheduling. The job is scheduled, and the job is completed. And look, we initiated our maintenance effort the moment we found the defect. Now, that doesn't mean we shut the plant down and fixed it. That just means we put it on the backlog. We let the planning and scheduling process start. And as our planning and scheduling process was working, this defect was down here getting a little worse and a little worse and a little worse. So by the time the work order was released for scheduling, the job was scheduled, and the job was completed, we're just here at the end of priority 3, but before we've hit priority 2, and you'll notice we never, ever got close to failing. We never found ourselves in a what do we do now situation. We never found ourselves in a you have to reschedule production because this machine will fail type scenario. We found ourselves in a very easy to manage and a very cheap to execute situation up here. The opposite side of that coin is when we do not identify our defects early in their progression defect cycle. When we're counting on archaic inspection methods like, hey, if anybody sees or hears or feels anything rough, let us know. So by the time that happens, we're towards the end of zone 2 on our P to F curve. We're likely somewhere in this priority 3, priority 2 threshold here. Now it's more of an emergency. We enter an emergency work order instead of a request. We expedite purchase request. We expedite parts getting shipped. We receive the parts, the job scheduling completed. We don't have time to kit the parts. We don't have time to plan the work a month in advance or schedule the work 2 weeks in advance. All we're doing is fetching parts and getting them in as quickly as possible and getting the machine fixed and interrupting production schedules along the way. So you can see we get to a situation here where maybe the machine failed, maybe it didn't. We don't know. Each situation is a little bit different, but what we are for certain of is that our planning and scheduling process did not work the way it was supposed to. And it all had to do with our work identification function of the work execution management cycle and not identifying work early enough in its defect progression to take advantage of all these planning and scheduling and CMMS tools that we have like SAP and all these neat things that we can do. Right, so that's what failure progression is all about. All right, so a little bit of failure progression. We'll get into some details, and then we'll wrap this thing up. All right, rolling element bearing faults, so outer race, inner race, rolling element faults, cage faults. We've talked about those already. I've showed you the equations. Here's what a spectrum looks like. Now, this particular spectrum is a manufactured thing. We made it specifically for our little seminar here, and we can tell here's turning speed of the shaft, and we can tell from the amplitude of turning speed that this machine is either out of balance, or it's got some angular misalignment, or it's got a loose bolt or something like that. But one of those three likely is the root cause of, or the cause of this amplitude of turning speed being so high. And so we don't fix it. We consider it to be too low a priority. We're not going to mess with it, so we don't mess with it. So guess what happens? If we leave that run long enough, we start to get these little peaks here. Now, you'll notice that these peaks don't have the little red boxes on them. These peaks are not synchronous to turning speed, and we'll have to explain that in a later presentation if somebody wants to do that one. But what we know is those are all related, and we can tell from the frequency of those peaks that this is a bearing defect, and specifically it's an inner race fault. And we leave that, we don't fix it. Well, guess what happens to the outer race? It gets damaged as well, right? So from a defect progression standpoint, this low frequency event, this imbalance we'll call it, or angular misalignment, it puts some increased radial axial forces on the bearing, which causes the inner and outer race defect to appear. Now, what happens over time is these non-synchronous peaks, these peaks that the arrows are going to be pointing at, they're going to get a little bigger, and then they'll start to get smaller and smaller. And as they start to get smaller and smaller, these other peaks that represent harmonics of turning speed, they'll start to come up. So what happens is when the non-synchronous peaks start to get smaller and those synchronous peaks start to get taller, what we know is going on inside the bearing is the spalling has propagated around the race. The bearing is starting to loosen up. So what's happening is the bearing's ability to produce these non-synchronous peaks goes down, and the bearing's ability to produce these synchronous frequencies indicating looseness starts to go up. Right? So that's a typical progression, and those frequencies match with an SKF 6311 for those of you who are interested in such things. Now, here is a bearing fault that was caught in stage 1. What you're looking at is the envelope demodulation data. So we're using an analyzer that's capable of finding bearing defects up in phase 1. And if I were to show you or let you listen to the ultrasonic signal, and we don't have time to do all of these, we'll just do one, it's going to sound like this. Now, what you're hearing there, let me stop that, what you're hearing there is we didn't catch it right when the subsurface fatigue began. We caught it a little bit later, and that's why it was louder, but you could start to hear a pattern developing in there, a pattern that probably wasn't there a month or two prior, right? But we were able to pick it up in zone 1, so it's a little bit later in zone 1. And we know that from the fact that not only is the ultrasonic signal loud, but it also has a pattern starting to develop. So if we go to zone 2, now we're into regular vibration data. We can see the non-synchronous peaks here in the spectrum, but the amplitudes are really low. And if we wanted to hear what that particular one sounded like, we could go listen, and it would sound like this. Now, hopefully what you heard from that is the total volume of the sound was down, and I didn't mess with my computer or anything. Total volume of the sound was down, but the pattern was very distinctive, and the pattern was quite rougher than the first one you heard. So these two are two really nice examples of failure propagation from zone 1 into zone 2 on the P2F curve. Maureen, have we had any questions, or are we trying to get through this quickly?
No, actually, someone just piped in with a question that kind of relates to what we were just listening to, but the question is, is it just misalignment and unbalance that is going to cause the high vibration in turbine bearings, or what is it that's causing those vibration spikes if it's not just those two things?
Well, I'm assuming we're talking about a turbine with rolling element bearings, because that's the type of bearings we're talking about in this webinar. For sure, imbalance and misalignment are some of the chief culprits for rolling element bearing defects in turbines. Probably more common than either of those, though, is water in the oil. Most of the lubricant systems on turbines, there's always water in the oil, and we're always fighting to get the water out of the oil. It's just a function of the design of the system. But I would say that the chief among the culprits for turbine bearing failures is water in the oil. Now, the imbalance does happen, the misalignment happens, but usually the misalignment happens after some type of maintenance event and we didn't get it lined up right. It's not like misalignment happens just out of the blue. And imbalance happens usually when it's been a while since we've let the turbine cool off, and we get this bow in the rotor, which kind of acts like an imbalance and a misalignment all at the same time. But these are they're not so rare that we shouldn't worry about them, but they're certainly not as common as water in the turbine and the lubricant oil. Water in the lubricant oil probably is the worst culprit of all turbine bearing failures, at least rolling element bearing failures. I'll share this with you. I know we're a little bit over time. I want to be respectful of everybody's schedule, so maybe we'll share one or two more slides and then we'll wrap this thing up. What we're looking at here is some ultrasonic signature, some infrared signatures from two vertical pump motors, and these two motors just happen to be sitting right next to one another when we collected the data. And you can see that the top of one motor is right around the bearing is 153 degrees, and the top of the motor sitting next to it right around the bearing is 119 degrees. And these motors were roughly the same size, definitely the same load, as a percentage, definitely in the same environment, should have been very, very close to the same temperature. So from a thermography perspective, we were able to determine that one of these motors has a bearing defect. When we collected the vibration data, you will see that the motor that had the thermal anomaly, basically the heat concentration, the hot spot, the motor that had the hot spot, the vibration data definitely reflected that the upper race, pure vertical bearings don't have inner and outer race. They have a stationary race and a rotating race. And we found that it was the stationary race, the lower race, that had the defect. And it was a pretty significant defect. So these four pictures here probably are my favorite in terms of showing failure propagation. And I'm going to call it the same machine, even though they weren't the same machine, but they're so identical. They're so close enough that we can consider them the same machine. So this winds up being a very, very nice example of what it looks like normal, which would be the one on the right, so 119 degrees Fahrenheit and vibration signature that looks something like this, and then what abnormal looks like. So we know that when the bearing defect gets to about 16 Gs or so, which is pretty severe for that type of bearing, pretty severe for most all type bearings, and we know it's the stationary race, we can look up here and we can see the corresponding thermal energy or thermal data that goes with that bearing signature. So I don't know of for me personally, I don't know of a better example that puts vibration data and thermography data in the same place at the same time, showing a nice example of failure propagation. So really, really powerful story associated with this particular slide. Belt tension issue. When we think about these technologies, we need to remember that all technologies have some limitations. Maintenance had just repaired something here. There was a brand new motor, and they called the condition monitoring guys. The vibration guy got there first and said, "Hey, everything looks great. No need for the thermography guy to check it." The thermography guy says, "Well, drove all the way out here. I'll go ahead and check it anyway." The thermography guy found this, and after they properly tensioned the belts, you can see it cooled off to this. So we had a 257 degree hot spot here. When they properly tensioned the belts, it dropped to 107 degrees. Now, what's interesting is vibration never picked this up, and vibration cannot pick up belts being overly tensioned. Vibration could pick up the belts being misaligned, could pick up the belts being too loose, but cannot pick up belts being too tight. So this is an excellent example of how there's no single technology that can help you identify all the different problems, and in this particular case, the belt tension problem, which in and of itself, not too big a deal, but belt tension problems lead very quickly to motor bearing and pump bearing problems because of the increased radial load that they were not designed for. So with respect to these technologies, and I'm going to skip this one, with respect to these technologies, it's all about finding those defects, but more importantly, it's about finding and eliminating the root cause of those defects, right? So what we want to, the lesson I'd really like you to take from this is we want the technologies to work in concert. And when they work in concert, then we can get the maintenance costs down to as low as they possibly can be. We can identify and eliminate root cause, and this gets us the maximum time to plan and schedule the work. Because what we want to make sure is we don't break one of the two, what I call unforgivable sins for reliability engineers. The first one is to fix the same problem twice, and the second one's not be prepared for a problem we know is coming. Those two things, those two statements, I believe, embody all that a reliability engineer is supposed to be. So if I'm sitting here and I have a misalignment problem that's causing bearing defect after bearing defect after bearing defect, and my mean time between failure on the bearing is, 6 or 8 months instead of 6 or 8 years like it's supposed to be, and I haven't identified that low frequency event that's causing that bearing defect, in this particular case misalignment, and I haven't dealt with that misalignment, then I'm really not very good at being a reliability professional. Because again, reliability professionals are all about not fixing the same problem twice, and then of course being prepared for problems that they know is coming. So, Maureen, went a little bit over, but
that's okay.
That's where we are.
Yeah, we seem to keep most of the group is still online. So one question that's come up a couple times, was wondering if you could talk a little bit about electrical fluting and kind of where you stand on whether that could be labeled as a failure, or what your thoughts are on that.
Oh, very nice. Okay, so electrical fluting, what we're talking about is there's some kind of problem in the electrical circuit that's creating an extra force inside the motor, and usually this force happens at 2 times line frequency. So what happens is the rotor is being electrically forced to vibrate at 2 times line frequency, and as the rotor is vibrating back and forth, of course the stator is not vibrating back and forth. The thing that takes the damage, the thing that takes the beating and gets damaged, of course, are the bearings, and you'll be able to see electrical fluting. In fact, we showed a diagram of electrical fluting in the previous webinar. You'll see all these little indentations, and they're very beautiful around the inner and outer race. They're equidistant apart. They're a little bit deeper in the load zone because of the extra load. And just like most bearing defects, the electrical fluting, of course, is not the problem. The electrical fluting is the symptom. It's a symptom of a ground problem in the circuit, which is pretty common. Ground wire gets disconnected or ground wire gets corroded away, and nobody pays much attention to it, and they don't mess with it. And when they don't fix it, of course, we get this extra electrical current, which creates this extra vibration, which makes the rotor bang against the stator, and of course, banging against the stator, it bangs against the bearings, and the bearings get damaged. Right? So if that's not what you were thinking of, please, whoever posed that question, send Maureen another note pretty quickly, because maybe we were talking about electrical currents grounding through the bearing instead of electrical fluting, and currents grounding through the bearing is not electrical fluting. That's another problem altogether that has another solution and another characteristic altogether. So, Maureen, did you get anything on that, or was that what they wanted?
Well, so far I haven't seen them chime back in, but I'm sure they will follow up after the fact if that didn't answer it.
Okay.
Let me just look here. I just put the screen back over to me, so I just want to see if there's a couple more questions here maybe we can get to before we pop off. Someone, I guess, is just talking a little bit more about lubrication and just kind of the importance of, maybe you can just drive home again the importance of a good lubrication program and what contamination might do, and just a couple more notes on that.
Yeah. Well, I mean, contamination, we mentioned it earlier in the webinar, contamination creates this thing called abrasive wear, where we get particles in the bearing or in the lubricant that aren't supposed to be there, and of course the lubricant wedge has a tremendous amount of force in it. Could be as high as 250,000 pounds per square inch inside the lubricant wedge. So if that lubricant wedge happens to get a hold of a contaminant particle and it gets wedged between if it gets lodged between the lubricant wedge and the outer race or inner race, it's going to take that piece of contaminant and it's going to gouge the face of the inner and outer race, wherever it may be. So in essence, we've skipped subsurface fatigue and we went straight to what the bearing would consider spalling, even though it's not a spall, it's a gouge that comes from, contaminants. So, and usually, there's not just one piece of contaminant in there, there's, hundreds of them. So as they get into the load zone and that lubricant wedge grabs it and starts digging with it, it just makes a mess out of the bearing very, very quickly, right? So it is extremely important, this idea of keeping our lubricant clean and dry and making sure that as we move the lubricant from one container to the next and from that container into the reservoir, that it be clean or cleaned with each step, to ensure that we're not purposefully, although unintentionally, but purposefully ingesting contaminants into our lubricant system. Right? So just the simple act of cleaning off the grease zerk before you put the grease gun onto the zerk and start pumping grease in there can make loads of difference in the meantime between failure of our bearings as they relate to contamination failures. Probably the number one killer for lubricant is water, where we're not we're not storing our lubricants properly, and we're allowing water to get into the bulk containers, and then when we take the lubricant from the bulk container and put it in the reservoir, we're actually putting the water into the system ourselves, or by not managing our desiccant filters on our reservoirs. As the reservoir heats up and cools off, it's going to suck in air, and when it sucks in air, if that air is humid air, it's going to suck in air and it's going to suck in water at the same time, and when that water condensates, it starts to mix with the lubricant, and then all of a sudden our lubricant becomes compressible, which lubricant's not supposed to be compressible. That's the way those systems work. So by letting water in there, we allow that lubricant to become more and more compressible, and we prevent that lubricant wedge from even being formed. So it all has to do with proper lubricant storage and handling techniques. Can't stress that enough.
Okay, well, I think just in interest of everybody's time, there's still some questions coming in, but we will definitely do everything we can to get those answered either by our staff or get some of these over to you, Andy, to follow up with some folks. But really good presentation. Obviously, it stirred up a lot of conversation and questions, which is always good. So we really appreciate you taking the time to come back and continue to teach all of us about bearing failures and how we can hopefully try to prevent them. And so that was good. Thank you so much.
Okay, no problem.
And great. So just a few more kind of housekeeping slides here just to go over with you guys that are still on. Just want to make you aware, I mentioned at the beginning that we had the recording of the bearing failure mechanisms part 1 on our website, and we'll certainly have this one up once we get it online. We'll notify you all, but our website is, hopefully you'll find a very good resource for all things not just ultrasound related, but a lot of good reliability tools on there as well. So please check out uesystems.com. You'll see all of our previous webinars on various topics from compressed air to electrical inspections. So not just bearings. We don't always just talk about that. So please check that out, and you can also see some upcoming training courses that we've got as well. We hope you'll stay connected. This is obviously one way that we like to get everybody kind of together and learning at the same time, but we do have some other ways to stay connected in between these webinars. We have our UltraProbe users group on LinkedIn, just another great place. Some of you that still have some questions, that's a great venue to post some of those that can really get some good dialogue going between yourself and your peers. We're all on there monitoring it, so we like to chime in, but it's always interesting to see how our different users might respond to certain questions. So definitely use that as a resource. It's a great networking tool, so check that out. We're also on Twitter, and we have our Sound Advice blog. So again, just trying to find as many different ways as we can continue to push content to you guys, help answer your questions, and really be a resource. So we hope you see us that way. Just a couple dates to throw out at you. Our next webinar, our last webinar of 2012, is going to be on December 12th, and Joe Gerlach with TEG is going to be taking us to the electrical side of things. So we're going to be talking about analyzing electrical sound files. I'm sure he's going to have lots of different sound bites that he's going to be playing and helping us really dig in on what it is we're hearing and what it might mean when we're doing electrical inspections. We also have our Ultrasound World Conference coming up May 6th through 10 of next year. It seems far away, but goodness, time flies, so it'll be here before you know it. So hopefully that's something you can talk to your supervisor about attending. It really is a great conference, and we're looking forward to it. And we've also got pretty much our whole 2013 training calendar sorted out between our level 1 ultrasound courses, compressed air classes, steam trap. That's all up there, so hopefully that'll help you kind of plan out next year's education for you. And I'll just leave this slide up for a little while so you guys know how to get in touch with us. You've got our email, our phone numbers, website again, and we thank you guys for taking some time this afternoon to continue to learn and keep those questions coming. We definitely will be sure they get answered, okay? So Andy, thanks again, and we'll let everybody go and have a great rest of the day.
Okay, Maureen, somebody sent me an email wanting a copy of the slides, and I told them that I was going to be getting them to you, and you're going to put them up somewhere, I guess, like you did last time.
That's great. We really appreciate that. Thanks, Andy.
Okay, no problem. Thank you.